Before we really jump in and do a calculation of the magnetic field, we need to understand the units. The SI units for magnetic fields are the Tesla, which we abbreviate capital T. Note that there are other units for magnetic fields, such as a Gauss, that are not SI. So make sure that you're always working in Tesla. If you look up any values, convert them to Tesla. And if you have a problem that happens to give you a magnetic field in a different unit, make sure you convert to Tesla. A Tesla is a Newton per amp multiplied by meter, and if you try to expand that in terms of fundamental units, you get something just really kind of weird and messy. So unfortunately, our units are not very pretty once we're to magnetic fields. We have a new constant that's going to appear in our calculations, and this is called the permeability constant, mu naught. And note that we express it not just as a decimal number, but as 4 pi times 10 to the negative 17. Why is that? Well, you're going to have mu naught divided by 4 pi occur very frequently, so it's really helpful to keep it in these terms. Note that it is very similar to epsilon naught, which was a constant you had in electric field constellations, and that's called permittivity. So I frequently will just call it mu naught and epsilon naught, since when you're new to this, the words permeability and permittivity sound very, very similar. Something else that is really helpful when we work with these new units of Tesla is understanding how many Tesla is a reasonable value. So at the surface of the Earth, simply from the magnetic field itself, you have 5 times 10 to the negative 5 Tesla. So negative 5 Tesla seems like a pretty small number, but that is enough magnetic field to make all compass needles point in the correct direction. So small value, but still detectable. A refrigerator magnet, such that you might have on a fridge at home, is 5 times 10 to the negative 3 Tesla, so 100 times smaller than the Earth's magnetic field itself. Now, of course, there are some very strong refrigerator magnets, but this is kind of a normal one. A laboratory magnet is something you're not going to typically have at home, but what I have in lab for doing specific types of magnetic field experiments. Now, these magnets are pretty strong. If you put a credit card next to them, the magnetic strip on your credit card would probably be ruined. These are now at 0.1 to 1 Tesla, and these are going to be limited, right? The Earth's magnetic field is the same everywhere. A laboratory magnet, there's a really small area of magnetic field. Finally, a superconducting magnet, which is really just about as strong as we can get, is going to be up near 10 Tesla. And if you wonder where might you find something like this, it would be an MRI scanner at a hospital. And you're possibly going to find MRI scanners that are maybe 5, 10, perhaps up to 14 Tesla. So please note that we will have some problems where we're talking explicitly about MRIs, so you might get values of about 10 Tesla. But if you're doing a calculation that isn't explicitly about superconductors and it's just about normal magnets, little loops of coil, you should probably be getting numbers less than 1. So please use that to check your work. So now let's actually start talking about how to do a calculation. And the first thing we're starting with is the magnetic field from a single point charge that is in motion. And this equation is called the Biot-Savart law, so named after some French physicist, so I'm sure I pronounce it badly. Note that there's 2 different forms we can relate it in. It is going to communicate similar information, but one actually is going to embed the directional information in it, and the other only tells you the magnitude. So the first one only tells you the magnitude. And we see that new constant here divided by 4 pi. Then we have q times v, and then sine theta. What is this angle? This angle is between your v vector, your velocity vector, and this r vector. R vector is basically the position of the point that you're trying to calculate b at, assuming that your charge is the origin. So if we make our charge the origin, then we have this positional vector, and it's going to make an angle with our velocity vector. That angle matters. And note that this theta is not just with respect to the x-axis, y-axis, or z-axis, it is with respect to whatever direction velocity happens to be pointing in. R in this case is just going to be the distance between these two. And note that this is giving us the magnitude. It's not telling us the direction. So one way is to use the right-hand rule to figure this out, and we have to use a slightly different right-hand rule. So there's a video posted on Moodle that's actually from the fall in mechanics, going through the basics of cross products and how you can use the right-hand rule to do the cross product. So I think the second form is slightly more helpful in that here you see that you have v cross r hat. So no longer does sine theta explicitly show up here, and that's because the cross product inherently has sine theta in it. Remember that this r hat has a length of 1. It is not, that's not how that's spelled, length of 1. And so it points in the same direction as r hat, but it really just has a length of 1. And so when you have v cross r, the right-hand rule will give you the direction from that, and that also tells you that the result of that will be perpendicular to both of those vectors. So I think this is a slightly more helpful way to write it, since your direction is then embedded directly in it, but you do actually have to understand what a cross product is. So please take some time to review that. We will go through that a little bit more in the next video and look specifically at the vector cross product, but you do want to review some of the basics. As I've warned you before, magnetism is inherently going to be a three-dimensional situation, and so when we go to visualize our fields in magnetism, it's going to be pretty tricky. So one way to do it is to try to do this angle view where you see what's happening in 3 dimensions. Obviously, most of us can't draw this very well. So this is one way to do it, but another is to start looking at specific views. Now, if you take a specific view and project it down, so you're only seeing a 2D view, you need to make it clear where that view is coming from. One of the ways physicists do it is they draw these eyeballs that show you where the person is looking. So if we look directly at the particle so that it's going away from us, we get this picture. We would say its velocity is into the page. That's what into the page means here, velocity vector. And if you use the right-hand rule to point your thumb into the page, or for you, into the screen, you see that your fingers are in fact turning clockwise, which matches the electric field. Notice that we have field vectors, right, that tell you about the field just at one point, as well as field lines. And field vectors are tangent to field lines. So as you are closer to the charge, you have a greater field. However, you also need to think about your direction. So if this is your velocity vector, then theta is going to be the angle that your point makes with it. So if we're out here, right, this is my r vector now, that theta equals 90. Now remember that for a cross product it's sine of theta, so that actually gives you maximal. If instead we think about this point, this theta is now less than 90. It's smaller, and so we actually get a smaller magnetic field. So it can be really tricky to draw these. Feel free to actually show it as a side view in 2 dimensions, and then this view either from behind or in front in 2 dimensions, but make it really clear how these things actually relate to one another. A few really important points. The equation we've just worked with only applies to individual point charges. So if you have a very long wire, don't just start plugging those parameters into the Biot-Savart. This really only works for individual point charges or tiny amounts of charge. So the direction and strength depends on a specific point in space. Where are you, how far away are you, and what angle are you at with respect to the velocity vector? So keep in mind that you can't just plug one value in and know what magnetic field is doing over all of space. One thing that's important is to note that velocity appears on the top. So if your velocity is 0, you do not get a magnetic field. Now note that if a charge is moving, it still does create an electric field, but right now we're focused on magnetic fields. Now lastly, if you want to, for instance, find the magnetic field from a bunch of point charges zooming around you like a swarm of bees, you would just find the magnetic field from each one and then add them up. So this superposition works the exact same way for electric fields. First find the individual fields and then add them up, keeping in mind that they're all vectors, so you must figure out the direction of each one before actually doing that addition. So a few spatial properties to note from this picture is that around these circles, the strength is the same everywhere, since the circle is centered on, or at least shares an axis with the point charge, the distance is the same at each of these points. The angle is also the same with each of these points, so that's why it's equally strong. We have a stronger field if you're perpendicular to the velocity vector, and that's again in this plane here, where you have an angle of 90, sine of 90 is 1. If you're closer to the charge, the field is stronger, right? So keep in mind that this field is stronger than that field. Don't think about the size of the circle telling you anything about field strength. Finally, your field is actually going to be 0 for points that are parallel or anti-parallel to the velocity vector. So that means along this line itself, B is equal to 0. And same for the points immediately ahead. So there are some points in space where your magnetic field is going to be 0. And note that that's again coming from the angle.